All right, let's talk about one of the most clever tools in the entire machine learning toolkit. It's called the Expectation-Maximization algorithm, or EM for short, and it's all about tackling one of the biggest headaches in data science: messy, incomplete, real-world data.
I mean, just think about it for a second. What happens when the data you need most, the stuff that holds the key to your whole analysis, has big, gaping holes in it? What do you do when the most important pieces of the puzzle are just gone?
For most methods, that's game over. The code breaks, the analysis fails, it's a dead end. But the EM algorithm, it's different. It looks at that missing information and doesn't see a problem. It sees an opportunity. It actually thrives on this challenge.
So to really appreciate just how cool this is, we first have to get on the same page about the fundamental challenge it was designed to solve. And that is the missing data problem. Because, let's be honest, data out in the wild is almost never perfect.
It's really a tale of two worlds. On the one hand, you have the ideal data set. This is the dream, right? Every single value is there, all neat and tidy. Analysis is a breeze. But then, there's reality. Not only are values missing, but you've got these hidden or latent variables at play. These invisible forces shaping your data that you can't directly measure. And in that world, standard tools just fall apart.
And this isn't some niche academic issue. It is everywhere. When you're trying to cluster customers, the actual group labels, that's missing data. In NLP, the true topic of an article is a hidden variable. In recommendation systems, you don't know a user's true preferences. You only see what they click on. In all these situations, the key information is missing.
So how in the world does EM crack this case? Well, the best way to get an intuitive feel for it is to think of the algorithm as a kind of two-step detective. It's a really great analogy for what's happening under the hood.
So here's the more formal definition. The EM algorithm is an iterative method. That word is key. It doesn't find the answer in one single shot. Instead, it gets closer and closer to the solution by repeating a process over and over again, cleverly working around all that missing info.
In that process, it's a beautifully simple two-step dance. First, you have the expectation step, or the E step, and right after that, you have the maximization step, the M step. That's it. Let's see what our detective is up to in each of these. Okay, in the E step, our detective looks at all the evidence they do have, and based on their current best theory, they make an educated guess to fill in the blanks. This is the expectation part. It's calculating the most likely or expected values for all the missing pieces. Then, in the M step, with a now complete data set in hand, part real, part guess, our detective takes a step back. They update their entire theory to find the model that maximizes the chances of seeing this data. They're basically asking, okay, given these filled-in gaps, what's the best possible story that explains everything? And this right here is the magic of the EM algorithm. It's not just guessing blindly. This two-step cycle is mathematically guaranteed to get better with every single loop. The likelihood that its model is right just keeps climbing, iteration by iteration, until it settles on a great solution.
Okay, enough theory. Let's make this real. We're going to watch the algorithm in action as it tries to discover hidden groups in a classic example using something called Gaussian mixture models. In this case, the missing data is simply which group each point belongs to. So here's our starting point. We've got this big cloud of data points. We think there are probably two groups in there, but we have no labels. We have no idea who belongs to what. So we do something simple. We just drop two cluster centers down randomly. It's almost certainly wrong, but it's a start.
Now for the very first E step, based on those two random starting points, the algorithm looks at every single data point and calculates the probability that it belongs to the red cluster versus the blue one. Obviously, points closer to the red center will have a higher probability of being red, and vice versa.
Next up, the M step. The algorithm uses those probabilities as weights and recalculates the best spot for each cluster's center. It's like finding a new center of gravity. The centers get pulled toward the data points that most likely belong to them, and they inch their way to a better position. And then, you just do it all over again. A new E-step calculates new probabilities from the new center locations. A new M-step moves the centers again. You just repeat this dance, E-step, M-step, over and over. And with each cycle, the centers get closer to the real heart of the clusters until, eventually, they stop moving. And just like that, the hidden groups are revealed.
Now, finding clusters in data is super useful, but that's really just scratching the surface. This ability to find hidden structure makes the EM algorithm a total powerhouse in a ton of different real-world applications.
So yeah, we talked about finding customer segments. But EM is also at the very heart of the hidden Markov models that powers speech recognition. It's used to reconstruct clearer medical images from noisy scanner data. It helps biologists find important repeating patterns or motifs in massive DNA sequences. I mean, the list just goes on and on.
But, as powerful as it is, EM is not a silver bullet. It's not magic. It's got its own set of trade-offs, its own blind spots, and it's really important to know what they are if you're going to use it effectively.
It's really all about balancing these pros and cons. On the plus side, it's a genius at handling missing data, and you're guaranteed to see improvement with each step. But on the downside, it can get stuck on a good enough solution instead of the best one. That's what we call a local maximum. And because its final answer can depend a lot on that first random guess, and because it can sometimes be pretty slow, you have to be smart about how you use it.
When you really step back and think about it, the expectation-maximization algorithm represents this incredibly powerful idea that we can find deep insights not just in the data we have, but by reasoning intelligently about the data we don't have. It finds meaning in the void, and it kind of makes you wonder, with all the messy, incomplete data out there in the world, what's the next huge discovery that's just hiding in the gaps, waiting for us to find it?